So I suggest that we begin our webinar and say you welcome for this meeting. Before we start, Jean-Luc wanted to say something. This one?
Yes, not only not only me, but on behalf of the three organizers. So we are only the 10th of January, so we wish you a very good and helpful and peaceful year 25.
With a nice picture of Lyon for the light feast. That's it?
Yes, so if you have an interest, we invite you to visit Lyon next year around the 8th of December.
That's it. Thank you. The program is as proposed. You have the first part on importance of data validation, and thanks to François Clemens. And then Jean-Luc Bertrand-Krajewski will present you the Urban Drainage Metrology Toolbox and the use of it for data validation. And you will have some time for concluding remarks and discussions. We really enjoy to welcome you. You're just only 34 persons, but 99 registered, from just a third from France, half from Europe, and a nice part from all over the world. And you have for half of registered people, scientists, and the other half is mainly practitioners of consulting, industrials, public organization, and water management services. So that's our objective for this webinar, and that is the general objective also for the Co-UDlabs project. The Co-UDlabs project within Jean-Luc and François developed the toolbox, is a collaborative urban drainage research laboratories community, and it gathered 17 large-scale research facilities from 9 partners from 7 countries. In fact, it's 7 research laboratories and 2 other structures that are more in knowledge transfer as Graie, and I am Elodie Brelot from Graie, I forgot to say. And Graie is for transfer as Euronovia, two structure of transfers. And the program is coordinated by the University of Cologne. The main activities of the Co-UDlabs project were or are multidisciplinary research, transnational access to the platforms, some training and transfer activities, and networking. And it ends at during the first semester of this year. You have 2 other proposals of meeting and of webinar, one on fair data, findable, accessible, interoperable, and reusable data in January 28, and the second one on the techniques for monitoring underground infrastructures in January 30th. And with regard to the network activities, the partners of Co-UDlabs organize an urban drainage research infrastructure network and a working group called UDrain within the Joint Committee on Urban Drainage. It has been organized and proposed in June this year, and there's already 36 contributors with research infrastructure from all over the world. And last information about networking, we will join a lot of people on urban drainage in Lyon in June 26th for next Novatech conference. So I just can say you that we hope to welcome you in Lyon in June if you don't come in December for the Light Feast. You will have all the information on the website of the program. We will send you the slides with the links after the webinar. So if you did record, you did register, we have your contact to send it to you. And that's all for me. Just saying that if you put your name, I can see if you're here. So please indicate your first name, surname on your identity. You can write the questions in the chat. And if there's a lot of questions, we will ask for our speakers to stop and to answer the questions. And I think that's all I had to say for introduction. And I give the floor to François. Thank you.
Elodie, I'll try to share my screen without technical issues. Let's see if that works.
I'm sure it will.
First,
I stopped.
Okay, do you see my screen?
Part of your screen, Bizarre.
Part of my screen.
Yeah.
Is it better?
Yeah, that's good.
Okay, well, thank you.
Perfect. Thank you. Thank you,
I saw quite a few familiar faces in the audience so far, so also for my part, a very prosperous 2025 for all of you. And I need to correct a small issue, Elodie, as you announced me as being working with NTNU in Trondheim and Skillsinmotion. The latter is still correct, though the first has stopped last September, and being an academic nomad, I'll be joining the Nanjing University of Information Science and Technology in the course of this year, just to be complete. So what will I share with you in the coming 40-ish minutes? So it's about monitoring and about data validation, this webinar, but a very important question to put forward first is, why would you monitor these systems in the first place? And then I'll show you some examples of the need for data validation and also the consequences if you don't. And that's a matter of realizing that some data are correct, but most data are wrong from a certain perspective. Then I'll try to convince you that data validation will help you. And I got a huge amount of concluding remarks because it's a very broad subject. So it's a bit of a hodgepodge of experiences I got in practice and in academia together. And I guess it's quite important, and I'm sure this will be shared with you, but Jean-Luc and I, we edited the book about 4 years ago now on metrology in urban drainage with a nice subtitle, Plug and Pray. You can download this for free. It's an open access book, so it won't cost you anything. And I guess it will give you some background information and at least a good entrance to the literature that has been written on this subject. Well, why monitoring urban drainage systems? Well, it is nice as an engineer when you design something that you can check if it works according to design. And also, you know that systems deteriorate. So just to make sure that your service level that you agreed in some contract or a document or a public legislation, that you are actually living up to the standards that are being set. So it is quite normal, in my opinion, that you monitor your system. Then in some more detail, you can also have to monitor for operational purposes like pump operation, and quite important nowadays is real-time control. So to change your system according to the needs that have been put upon the system. And of course, very in focus over the past decades, I would say, the environmental impact, like the effect of CSOs on receiving surface water bodies or leakages into groundwater, which is also going to be put in some European legislation in the course of the coming years. So you'll be obliged to monitor this. Then there are also legal and or accountability reasons, like living up to permits, or you may have contracts with commercial parties. So you need to make sure that you live up to the agreements that you made. A very important and well-known thing to monitor is the technical condition, like the famous CCTV inspection technology that has been deployed all around the world, I would say, over the past decades. And very important and often overlooked, just to know, what are you managing? What is there? Where is it? And what kind of dimensions are your system? Then if you look, I guess if you are involved in urban drainage, in whatever role you take, it can be manager, it can be a consultant, it can be an engineer. What you're constantly doing is taking decisions. And what you normally do in the ideal world, you have data, you extract information from these data, you analyze this information, you come to a certain knowledge of the system. This may lead to understanding, and based on this understanding, considering the rest of the urban environment, you take a decision. Now, in my experience, a huge amount of effort is being put in the software and the protocols and the training of people in extracting information from data, how to analyze data, and how to come to decision using decision support systems. But validation of data is often overlooked. Now, if you take a look at the quality of the data that we use in urban drainage, it's often, well, let's say, suboptimal. So if you know that your data are wrong and you apply perfect logic, you've got a serious risk of taking a wrong decision. Now you can take two courses. You can say, okay, let's put some errors in our reasoning so we may reach a good decision, or you may try to enhance the quality of your data. Now, I'm not much of a gambler, so I would like to have a correct idea of the quality of the data on which I base my decisions. So let's see how this works out. What is the data need in urban drainage? And I'll take the freedom to do some advertisement here. Last year, there was an open access book on asset management and urban drainage published. You can see it here. You can download it using the link indicated in the sheet, which will be shared again. And in this book, there is a big chapter on data management, and that goes a little bit broader than just monitoring data, which has been addressed in the metrology book in very much detail. But if you look at the data need from the perspective of an asset manager, it is very handy if you know what you are managing. So what pump is where, what pipe lays where, how are the pipes connected, what manholes do you have, what kind of contributing area do you have to your manholes, etc., etc. A second question to be answered is, okay, what is the technical condition? And these two categories are semi-static data. They change in the course of years. While how does it function, and that's the main issue that Jean-Luc will address in this presentation, is dynamic data, and that can change in the timescales of 1 minute in some cases. So I would like to focus a little bit on the first two in relation to the third question to be answered. Now, this is an example of, do I know what I manage? And if you don't know, as was the case here, somebody takes the decision to dig a hole. And because he has been checking the data and there were no pipes, according to the data he or she had, to the decision we are going to dig a hole around here. In the process, a big pressure main was hit. And the circumstance was that next to this pipe, there was also a high pressure gas distribution pipe. And this led to a situation that caused a huge amount of damage and hindrance, as it was also close to a highway. So the highway was closed for a few hours, and there was a huge amount of repair business going on. So only because somebody typed in a wrong number on the location of a pipeline. So this may underline the importance of validating the data of the system that you're managing. Where is what? How does it look like? Another important issue, of course, is the technical condition. And as you may know, asset management on sewer systems or urban drainage systems was only a topic starting in the 1980s. And one of the first things people did was putting a camera into a sewer system and to see what it looked like. Well, they were scared to death. I can remember headlines in the newspapers in the 80s that everything is going to collapse and we need to do action. Well, in the end, it wasn't that bad, but it resulted, at least in Europe, in a very fast development of technology of CCTV inspection of sewer systems mainly, but also to standardize this. And the standardization was a bit too early, in my opinion, because when we evaluated the resulting data after 20 years, we saw that because there was a kind of human interpretation of images, that on a scale of 0 to 5, we had deviations of 2 classes, while sometimes decisions were made that up to class 3, 4, and 5 should be replaced, while there was an uncertainty of 2 classes up and down. Unless, when this was realized, we checked twice. So there was a kind of data validation being done on the inspection data, reducing the uncertainty and the systematic errors in these data, which saved us a lot of money. Around 2010, we noticed that from these visual inspection data, about 25% false positives. So people saw defects that were not there on second evaluation, which also led to a huge amount of money being invested replacing pipes that were in perfect order. So here again, data validation did help a lot. And what helped also was the introduction of artificial intelligence. It's been a big topic about since the last 10 years. And as we look now, the application of artificial intelligence and image processing has reduced the number of false positives to only 5%, which is quite a good achievement, I would say. Alas, there is still no good solution for the uncertainty in the classification system. Another conclusion was that the standard we use in Europe is far too detailed. It has too high a resolution. Very, very boldly stated, people are expected to distinguish between 75 different defects and scaling them on a scale from 0 to 5, while it is known from psychology that when people are looking at an image, you're able to remember up to 7 different aspects in that image, which is also true for X-rays studied by medical doctors, just to scare you a little bit more. So it's just an accuracy that is not feasible. And it is nice to compare this to, for example, the Japanese standard. People have acknowledged it there, and they only have 3 classes, and they have a far more consistent result in their CCTV footage. So there is some work to be done, and in my opinion, setting a standard too early is hampering development, or at least it is slowing it down. So if we come to talk about standardizing data validation, I would say think twice and don't go into too much detail. I'll come back to this later on. And another issue is that the CCTV standard, or say the standard for visual inspection, it is measuring the wrong parameters. It is not measuring any physical quantity. So basically, we are looking at a standard that is promising things that it cannot really realize. And I guess we should try to avoid this in future standards. Then we come to the assessment of the actual performance of a system. And that can be a huge amount of things. And one of the most important, I guess, when looking at urban drainage systems, is protection against flooding and try to minimize environmental impacts. And this is often judged in practice by consultants and practitioners by using hydrodynamic models. And these models are quite often applied without any validation. And validation is, in my respect here, to be sure that your basic data are correct, that you have the right pipes in place, that you've got the right contributing surfaces in place, etc. And then I don't even mention the calibration, that is tuning the model parameters that you are using. That can lead to substantial differences. I showed some examples here at the bottom. For instance, in many cases, you assume that there is one roughness value for each pipe. In the middle, this image here is an image of a pipe that is 90 years old and has been suffering from crown corrosion. And we've been measuring the actual roughness. The interesting thing is that the bottom part, which has been contributing dry flow, had about a roughness of about 1.5 millimeters, in line with what we normally use in the models. But the top part has a roughness of 12 millimeters, which is a tenfold, which results in a drop in the capacity of this pipe by almost 50% during storm events. At the picture at the right here, you see that is fat being stuck to a siphon, reducing the capacity of the siphon a lot, resulting in excessive flooding. And if you know these things, then it is far better to clean out the siphon than to build a second one, which is normally done when flooding occurs. Here's another example that We also assume when we are modeling a system that the pipes are completely free. And we had a big project in the municipality of Utrecht, and we noticed that the system was behaving completely different from the model, but really completely different, up to deviations of 50 to 60 centimeters. And when analyzing inspection data, we found out we got root intrusion. And then we tried to model the root intrusion, and the model was in line with the measurements. And when we cleaned out the system and recalibrated, it was still again in line with the model and the measurements. So this gives a clear indication that measuring on the processes, in this case the hydrodynamic behavior, the quality of the data and the usability of the results depends a lot on the quality of as well your data on the geometry and structure of your system as on the technical state of your system, highlighting the need to validate all data that you use in the process. Then there is another way of validating, that is, for instance, if you got a pump station in a wastewater system, these systems often suffer from blockage due to fat accumulation. And there is a kind of, let's say, religion or different religions on how to design pump sumps, because the geometry and the combination with the location of the pump and the discharge is defining the accumulation of fat. So many of these systems are being modeled by CFD, and nowadays you can put quite advanced measurements in place. This is an example of a measurement using PIV that is used to check the model. And now the question is being put
Jag
forward.
skiftade faktiskt till dator.
I'm sorry? I'm sorry, I heard some question. Can I proceed?
No, I think he thought he was close, but it's nothing.
Ah, okay, it's nothing. Well, what you see here is a very advanced measurement called PIV. It escaped from the laboratory about 10 years ago and is now being applied in practice. Validating these data is, I wouldn't say impossible, but very, very hard. Even in the lab, validation of PIV data is terribly difficult. So this implies that if you're going to validate your data, that you need to understand the whole measuring system. I'll come back to this as well. And then the environmental impact is a very important issue. And obviously CSO events serve as the default example because they are the result of utter overload or dysfunctioning. For instance, if you got a design flaw in your system, you'll have CSOs on a scale or a frequency that you would not expect. So measuring these is a very important activity to validate the model and the beliefs that you have in how your system functions. But it can also reveal poor management, like, for instance, the occurrence of CSO events during dry weather periods due to pump malfunctioning, which happens a lot. What you can also do if you measure or, let's say, monitor these events, you can have some idea about the environmental impact of malfunctioning of your system on the water quality compared to other sources of water quality problems. It has to be said again that, of course, CSO is a very important thing being put into legislation. A very nice example at the moment is Great Britain, where it is a big issue. And it's often related to legislation, and in many cases, there are sometimes demands being put forward in legislation that are not realistic. For example, we had a proposal in the Netherlands a few years ago that water boards wanted to have a 95% uncertainty level of 5% in the yearly CSO volumes, which is maybe feasible under lab conditions, but in field conditions, I won't say it is impossible, but it would cost a huge amount of money. And then you can start talking about the cost effectiveness of this kind of legislation. So if there are people in the audience who are writing legislation and you want to, let's say, put demands on the quality of measuring data, you're correct, but please be realistic. Here's another example of how you can use process monitoring for checking on the data on your system structure. I'm not sure everybody is familiar with what we are looking at, but this is a stretch of stormwater sewer. And here you can see site connections. And each number is a known connection to the stormwater system from houses or buildings or whatever. And what we have done is we put a glass fiber in the stretch of sewer, and we've been measuring the temperature every 2 minutes, every 2 meters. And as you can see, there are regular releases of warm water. So red indicates about 25 degrees and deep blue indicates 10 degrees Celsius. And you can see that, and this is the time, you can see that there are at regular intervals, we got discharges of warm water. And that indicates there's an illicit connection. The interesting thing is that you can see that these discharges correspond to location number 17. These discharges to number 22, but there is apparently an unknown connection to the stormwater system between 23 and 24. So in this case, in monitoring the functioning of the system, we have 2 things in one blow. We have an illicit connection at a location that is not known. So this implies we have to do 2 things, that is change our database or update our database, but also try to avoid these spills into the stormwater system. Well, what is the origin of imperfections in measurements? Well, I guess that is something you can also read in the metrology book. We got a nice plethora of different reasons why things can go wrong. And maybe the best summary is Murphy was an optimist, because everything that you can think of in theory is being blown away by practical things that you can't imagine. I have some examples here, but you can read the text for yourself. These are 2 pictures for monitoring project I've been doing. And this project on the left, I gave order to a company to install some rain gauges. And I forgot to tell them, don't put them under a tree. Well, of course they did. So we got quite weird results, and there was hardly any rain over there. Then, learning from this experience, I instructed them, now you need to build a very specific setup, as you can see on the left, which was put in a park that was only could only be entered while paying entrance. And it was the default setup of a rain gauge. And to my amazement, 2 things happened. There was a huge storm event almost every Saturday night. And the Monday after that, the rain gauge was smelling to urine. So it was being used as a urinoir for one thing. And somebody found it nice to put gravel into my rain gauge. So these things that are beyond your control to a certain extent can hamper the quality of your measurements. And apart from that, at a certain point, I had a project in which I had routers being installed in lampposts. And on a nice Thursday morning, one by one, the signals went away because the municipality has decided these are not mine, and they took out all the communication devices out of the lamppost, and my signal was gone. So there are many, many ways that things can go wrong. And if you're going to be in data validation, you need to have a kind of degree in being a detective. You need to think, how can things go wrong, and try to find out why it went wrong in a specific case. Well, data validation is basically checking if the obtained monitoring data are correct, which is strictly speaking impossible, because that would imply that you know the real values and you don't know them because you're trying to measure them. So the issue is that you need to make sure that the data you got are plausible and make them as plausible as possible. And remember, and I'm pretty sure that Jean-Luc will also come back to this, but data validation encompasses the whole monitoring system. So not only the sensor of your system, but also the data storage, the data transmission, and in many cases, without you being aware of it, there is some inherent post-processing going on in your data acquisition system. And all these steps has to be taken into account when doing the data validation. And the big trick is if you see deviations to find out where in the process things go wrong and are you able to correct it, yes or no. So we have to retreat to obtaining a level of, I would say, plausibility, because validation is basically implying the truth, which is unknown. So when you look at physical realistic data, for instance, if you're measuring water levels in a sewer system that are below your lowest invert level, you got a small issue, I would say. And these things may happen as sensor drift is a very common feature that happens. And of course, you can have other data sources to compare to. For instance, if you had some flooding, you can be pretty sure that on the social media you will have some messages about we saw flooding between 1 and 2 on this and this location. You can use that as a kind of rough validation of the measurements you obtained on that location in your system. Well, why is data validation helpful? Well, maybe a small thing. The graph over here is a graph I use many times in monitoring projects. And basically, it's simply an Excel sheet. Don't try to read it. That is pointless. But each line is a sensor, and each column is 1 day. And the green indicates that after validation, 95% of the data is assumed to be correct. White, there is no data. Yellow, 50% is correct. And red, less than 50% is correct. So this gives you an overview of in which time windows you got usable data for, let's say, model calibration. So if you had to choose to calibrate your model, you preferably use as much data as possible, so you would go for the time window that has only green cells in this case. But it gives very much information on the effectiveness of your monitoring system. I've been keeping track of this. I started my first monitoring project back in the 1990s. And in those days, we were really, really glad if we were able to have a 50% data yield on water level, that is. While at present, it's fairly easy to obtain a 99% uptime, and about 95% of the time correct data is possible if you do it correctly. As I said, it's very important to find the cause. Why are data missing, or why are they incorrect? So you need to be a bit of a detective. Sometimes it's fairly easy, because if you see a sudden shift in your water level, and you can link this to the moment that somebody did some maintenance, it can easily be that you put the sensor not on the right reference height. And that can be correctable, so you can curate your data afterwards. And that should be indicated as well, by the way. But being a good detective, so understanding how your system functions, understanding how your monitoring system functions, may help to increase your data yield. What's very important with respect to data validation as well, it is not something that you only do when you are monitoring. Also, when you are going to design a monitoring system, it's very important to keep in the back of your head that you will need to validate your data. And it can be done, for instance, by making sure that you got, let's take water level as an example again, that some sensors are overlapping, so that sometimes they will measure more or less the same water level, which is a double check on both of them. It's also quite important to give thought how to synchronize all measuring stations. You can choose for having one clock for each individual sensor, or you can have one clock for the whole system. The former is easy, the latter is more complicated, but if you ever bought a clock in the shop and you've seen 1,000 clocks, you know one thing for sure, they're not running at the same time. And to my amazement, if you buy, let's say, 5 sensors of the same manufacturer, and you start them at, let's say, Monday morning at 8 o'clock, you leave them running, sometimes within a week, you got a 10 minutes deviation. And 10 minutes deviation, when monitoring the rapid processes during storm events, is yielding your data unusual. So the message is data validation is something to reckon with already when designing your monitoring system, and also when you are going to buy your equipment. Well, there is no formal standard for data validation in urban drainage, and I applaud that for now, although the benefits of having one would be that you could have standardized tools for validation, which would improve the quality of monitoring data in the long run, and would also be very, very helpful to share data between practitioners and between academics. And this would really, really help us to move forward in developing tools and developing educational bases. So I'm a bit double here. On one hand, I would like to have some standard. On the other hand, as I said earlier, standardizing too early is going to stop developments. We have to realize, and I've seen this many, many, many times, you start a new research project and the first thing you do is spend 2 years and half of your budget in designing a monitoring system, putting everything into place, get everything operational, then you can measure for a few months, and then your project ends. So if we would have this standard, we wouldn't have to do that all over and over and over again. And also sharing field labs could be very helpful here. And in Co-UDlabs, we at least try to highlight this. Well, if you are looking for a more or less systematic approach, what would this encompass? Well, I guess it would be very good to define the levels, different levels of data quality and levels of data yield strived for depending on the purpose of use. For instance, if you are going to monitor CSO events, it is no big disaster as sometimes you're missing 5 minutes of data. Or if your data are 2 or 3% off, that's not a real issue. While if you're trying to calibrate a model, having data gaps of 10 minutes or deviations up to 5% can be deadly for the result. So we could have some kind of, let's say, a list of different goals to use this monitoring data and a kind of indication of what kind of demands you should put on having data being useful for the goal you're looking for. And also help people or give some guidance how to find the cause of declining data quality and data yield. Very important when you start on this is that you are sure that the validation process is completely, well, let's say almost completely developed before the data come in. And that would imply that you got all your tools available and that the personnel is trained to use it, and also that the personnel is trained to go into the field and try to find the cause of deviations. What's also quite important, and I learned this the hard way, as I once went to a municipality and had a discussion on monitoring. And after a year, I received a letter with 2 CDs. Mr. Clemens, we followed your advice. We put sensors into the sewer system. Can you analyze these data? Well, I looked at the data. Indeed, they put in the sensors. And after 2 weeks, all sensors went on 0 because they put in the sensors, never looked at them. And after 2 weeks, the batteries were gone and there were no data. So a regular check is quite important to make sure that your data yield is sustained over longer periods. Another thing that would be in a systematic approach is to make sure that you store the original raw data, because it happened quite often, in my experience, that you use software to validate or process your data, and after a year, some bugs are being discovered. Then it is a good idea to have the original raw data and reprocess them. So these are some aspects in data validation standards that should be there in place. Then a question coming up quite often is curating data or repairing data. Well, in my dictionary, from a scientific point of view, that's a death sin because you are inventing information that wasn't there. On the other hand, in some cases, if you are looking at real-time control, for instance, and you got one missing data point, maybe you can say, okay, let's simply make an interpolation. But there are some limits to this. And whatever you do in curating data, make sure that you label it, this data was curated or interpolated, and also mention how you did it, so that if somebody's going to use the data, at least he or she is aware of the pre-processing of these data. Well, so I'm almost through, I guess, Elodie, in time. You're muted, I guess. Well, I'll just go quickly through them.
Yeah, go.
Okay. Well, we have to realize that large-scale monitoring is possible over the last decade. And we have now quite robust sensor technology, IT technology has progressed, and the availability of cheap components makes it look easy. So anybody can do this. Simply throw in some sensors in the source system and there you go. But that may be a very deceiving perspective. And I would like to urge everybody, if you start a monitoring project, take it seriously, because when you spend a lot of money and time and nothing comes out of it, your manager will be quite displeased, and that will avoid having other monitoring projects in the future. On the other hand, the need for monitoring is increasing as we are faced with rapidly changing conditions, like climate change quite obviously is affecting our systems. We need to know how to cope with this. We need to know how our systems react to these changes. So the need for monitoring is increasing. And it should be done quite well, because we're looking at the large-scale adaptations that will cost a huge amount of money. So referring back to my system from data to decision, let's make sure that at least the data we're going to use for these decisions are as good as we can get them. Well, I guess I'm repeating myself. Data validation asks for the awareness and acknowledging the limitations of measuring systems. Not everything can be done, and not every monitoring system can be validated, like, for instance, this PIV system. And you should be very aware of the source of possible errors or deviations in your data. On the other hand, it is quite important also to realize that data validation is serving to enhance the quality of all the data we use. So not just monitoring data, but also the data on the technical status of the system, and also on the dimensions and the structure of the system as they go hand in hand. Very important, when doing data validation correctly, you can reduce damage or hindrance due to malfunctioning, operational mishaps, digging in the wrong place, and, as I said, damage due to digging and tunneling activities. I would like to leave it here.
Thanks, François. It's you on time, just 2 minutes. So it's
Wow.
perfect. Perfect.
Sheer coincidence.
We plan a short coffee break, but there is a question not on standardization of validation, but data standardization. And if Agnete Pedersen want to open the question, and then we will have a break. Okay. Agnete?
Yeah, can you hear me?
Yes.
It's because I am from Utility VCS Denmark, and we have started the discussion along with a lot of other utilities, because we think that that there is a too high, the cost is too high of not having standardization of data, because we use a lot of different systems and tools, and we cannot compare stuff, and also we cannot procure and test stuff as fast as we want to. So we would like to know, how can we speed up this standardization of data? Is it by regulation or by if we change our procurement agreements, or if we work together, all of the utilities? And also, like you say, you are not to speed up standardization, but when is the right time to standardize then?
That's a very good question. Thank you. That's a very good question. And I guess you should make a differentiation between what type of data you're going to standardize. Like if you want to standardize the description of the system, so let's say, manholes, pipes, pumps, infiltration systems, etc., that is doable. But there is a nice example going on in the Netherlands. 10 years ago, we started a big project of standardizing all these data for all of the Netherlands. And this project is now in place. And that implies that at the moment, I guess at the moment we got about 80% of all municipalities have all their data in this data model. And they're also accessible. And now people are working on also inspection data and on monitoring data to standardize it. And the big plus of this is that sharing data between different platforms is much easier. But what was not happened, we did not standardize the software, but we standardized the data model. And that's a very, very different approach, because that implies that everybody agrees what is water level, what is diameter, what is the type of surface. If you want, I can provide you with a link to this project, and that may give you some indication. The big trouble is that it is one of the possible standards. Because as you know, there are quite some commercial standards of people that are supplying software that de facto are a standard used by consultants. As far as I know, Netherlands is the first national standard model for this kind of data. And what is the right moment? I guess if you believe in Murphy as I do, you can only say that this afterwards, and you can't go back. I hope this answers your question, at least partially. Okay,
so I think it's a big discussion, and I think the second question is a big discussion for the end of the meeting for Stadachev. So I suggest coffee break, and we come back at 3. Are you okay? 10 minutes, 9 minutes, in fact.
Perfect.
Okay, see you at 3.
So welcome to the second part of this webinar. After François, I will go into some more details about some ways of proceeding with data validation with time series of data you can collect on your systems. And after some introduction of topics and some rules or algorithms we may use for data validation, I will illustrate its practical application with an example using the urban drainage monitoring toolbox we developed in the Co-UDlabs project. So this toolbox will include different menus. I will explain later on. And at the moment, it's enough if you know that it's a free toolbox. You have two options. Either you can use an online version or download a setup file and install it on your own computer. Everything is available on this link. And on the same link, you will also find user manuals, training files. So exactly the same files as shown in the user manual. So you can repeat yourself what you read in the user manual. So it's a kind of self-training mode of learning. The tool is available in English, French, Spanish languages. We expect to have German in the next month. And both offline and online versions will be updated until the end of the project, which will be April 25. You will see later on that everything is based on use of CSV files, and all of them are described in a very detailed format. It's like any other software. If you want to use it easily, you need to follow some rules about dates formats, data formats, and things like that. And there is an email address for communication for any needs, questions, remarks. The user interface you will see later is as simple as possible, but also as complete as necessary. So it's kind of compromise we had to define. It's designed or aiming to target both researchers and practitioners. Even if you use the online version, it's totally anonymous. So your data are not collected. There is no savings of your files on the internet and so on. So it's a really completely clean process and clear process for the users. And everything which is produced by the software can be saved, recorded, and read by the users. So everything is accessible to the users. Okay, it was already said. And in addition to the previous information, at the end of the project, of the Co-UDlabs project, all the files and the data will be available on Zenodo. Even the MATLAB source codes will be there. So if anybody is interested to further develop the tool, it will be open for this. How the tool is related to the metrology best practice. Imagine you have a sewer system or sustainable urban drainage systems too, SUDS or traditional Graie infrastructure. You will collect raw data by means of sensors, for example. And you will import this raw data on your, let's say, computer. And then you have to transform this raw data into corrected data. And this correction is based on the calibration of the sensors and on the calibration function you have established previously. It's just a reminder that no sensors should be used without previous calibration. And in this phase of correction, we also introduce two parts of the uncertainty propagation: the uncertainty linked to the sensor calibration itself, and the uncertainty to the site measurement conditions. Then, after the data have been corrected according to calibration uncertainties, we can proceed with the pre-validation step, and it will generate pre-validated data. And this is in this step that the tools like UDMT are interesting to make the pre-validation automated. Because if you have only a short data file, it's easy to do it manually. But if you collect, as we do, for example, data every minute or every second minute over years with many sensors, it's impossible to do it manually. It's too much time. So we need tools to automatically pre-validate the data. And no tools, no algorithm is absolutely perfect. And it means that after the pre-validation, a human being, a user, has to validate the data, especially to make final decisions. Because if data have been pre-validated as correct or rejected, usually it's easy, but there is a third category, which are the doubtful data. And this is where the manual final validation is required to help to make the final decision where you have still ambiguity or doubt. Once you have validated data, you can, if necessary, fill some gaps, as already presented by François. It's not systematically necessary, but for some applications or uses of your data, you need one value every minute or every 10 minutes or so. So you need to fill some gaps, but it's always very risky because, as François said, you generate something you don't have. So you should do it very carefully. And there are some substitution filling instruments or methods you can apply. And once it's finished, then you can go to your data processing and enter into the knowledge and information steps François described previously. And at these different moments, you can export your data to work with them. And for all these steps, you will need different tools and assistance softwares. And what is the topic of my presentation today is this part of automated pre-validation test. Another key point to have in mind is from step to step, you should generate another file and never write on the pre-existing one. It's the only way that you can preserve the traceability. And if you need sometimes to go backwards because you have new information, new knowledge, oh, I have to change my rules of validation, then you should be able to go back to your previous steps and reprocess the data. If you have not generated one file per step, then it's impossible to go back and to reprocess your data in a proper way. And the philosophy of the Urban Drainage Metrology Toolbox is to mimic or to reproduce this metrology best practice approach. So you will have all these steps, And if we go to each main screen, so this is the main screen for sensor calibration. So you have different methods to calibrate your sensors, from ordinary least squares to Williamson method when you have to include uncertainties in many coordinates. You can use different types of functions. You can force your calibration curves to go by 0 or not. So you have a very open tool to make your sensor calibration or sensor correlation. Once you have generated these corrected data, these calibration functions, then you can make the step of data correction. So you have to import your time series. You have to select the function data you have generated in the previous step, and then you generate a corrected data set. Then you have another block of functions to deal with uncertainty assessment, and you will be able, by using UDMT, to apply all the methods which are described in international standards for uncertainty assessment, from type A method, when you have repeated measurements. You can apply the type B method, which is also named the propagation of uncertainties, and you can also apply the Monte Carlo method. So you have all these possibilities, and you can apply these various methods to your own data sets to propagate all the uncertainties to your final calculations. For example, you have uncertainties in water levels, in flow velocity, and you can calculate the resulting uncertainties in your discharge values, for example. Data validation, this is the main topic of the day, so I will go further in details. And the last part of the UDMT is a special menu of tracing experiments, which is very good methods to check some flow meters on site. So I already explained why we need assisted or automated data validation. We are facing more and more larger amounts of data, so it's impossible to do this manually, line by line, too much work. And the other interest in having an automatic process is you avoid operator subjectivity. So if I do the validation and if someone else is using different rules, different methods, then we can never agree on what is a valid data or what is a non-validated data. So the interest of automatic algorithm and functions is it formalize and make everything objectives and transferable to someone else. I repeat again that there are two main steps: automatic detection of abnormal, doubtful data, and then a human being should always come to make a final validation. So I have provided a few examples to illustrate my presentation. So this is the data we measured some years ago in Lyon. So this is the water level in a sewer system. So this is a daily pattern you can recognize here. Sometimes there's a higher peak in the morning. And here you can find much higher peaks, which are due to storm events. And when we know that there are storm events, we know the rain intensities, we can conclude that globally this time series is not bad and that we can work with the data. Maybe there are some points here, but globally it's fine. Unfortunately, we cannot collect always such data sets. And what we are facing, for example, is another example. It's on the same site. So you recognize the daily pattern, but you have these strange peaks. Only during the day. They never happen during nights or late in the evening. We still have some storm events which are superimposed to this dry weather pattern. And we needed months to discover the reason of this. And after some months of investigations and asking questions to the sewer operator, the different teams of sewermen, we finally found the explanation. 2-3 kilometers upstream, they were testing some flushing gates, generating waves and these pulses. And these pulses were reaching our monitoring locations, and we were able to detect them. But it's important to know that if you want to validate some data in a given location of your system, you should be able to have the information about all the upstream action activities on the catchment and along the sewer pipes. If not, you cannot interpret what you have seen. So at the beginning, we rejected this data as unrealistic. But 7-8 months later, when we got the explanations, said, oh, these data are correct. So we went back to our process, revalidated the data again, and they were accepted because these data were now known to represent something true in the sewer system and not wrong behavior. Sometimes you have erratic behavior. Well, I've named that erratic, but there is no way to interpret it. There is no reason upstream to understand this behavior. You have these strange peaks, sometimes single values or 2 values in a row, and we were unable to find any reasonable explanations. So obviously they were discarded and rejected for further analysis. But how can we detect something like that automatically? That's the question. Sensor drift. So you have, again, a daily pattern, and you see that the night minimum values are increasing, become more or less stable. Then after more or less 1 week, it goes down again and change. And again, we needed some weeks to understand this process, and it was due to the clogging of the sensor, which was a pressure sensor. And after each cleaning, you recover a correct value during the night, but then it's covered again by sediments, and you disturb the minimum value you can measure during the night. And so it's also interesting to find ways to detect long-term drift, because this one was on a weekly basis, so it's easy and fast to detect it. But when it's more progressive over weeks, months, it's not always easy to find something like that automatically, at least. So we developed some tools for automatic pre-validation, and we generate for each test we do, we generate a mark, a pre-validation mark. And we decided to go with 3 possible values. Either the test is positive and the value is considered as satisfactory or accepted or valid. Number 2, you have a doubt. Your value is not completely impossible, but it's unrealistic or infrequent or unlikely, but could be possible to some extent. So you will give a mark 2, and this is this category that requires a final validation by a user. And the number 3 is for false or outlier or rejected value, because the test says, so it's not possible that this value is correct. And this is the 3 categories we have generated at the end of the pre-validation phase. And then the user is invited to make a final decision about all the values which have been marked with a 2. And the idea is, after this final manual validation, you have only 2 categories: valid values that you can further use for information, knowledge generation, or you have non-valid and rejected values. It's possible in the literature to find other methods, for example, giving some percentages. But if my value is valid with 60% of certainty, I don't know what I can do with it. So we decided to go for a much simpler information at the end. You have sufficient reasons to keep it and to say that this value is correct, then it's a valid value with mark 1. Or at the end of the process, the doubt is too high and it's recommended that you reject it as a non-valid value. What is very important is traceability. For each step in your process, you should keep always the raw data. You should have a record on a file where what are my the algorithm I am using, what are the numerical values I have applied in my pre-validation. So everything can be traced, can be modified later on, because you have acquired new information about your system, your sensors, your monitoring point. So this is really a very, very important point. And I agree, we know it will generate more files, it will generate more megabytes of data, but I would say it's the price to pay to have something you can trust in later on. You can imagine many tests or algorithms for this pre-validation. In the UDMT software, we have decided to keep only the most basic ones. It's not the ultimate tool in the field. It's only a tool we developed to promote the data validation, the best practice in metrology. And we have decided to go for 8 pre-validation tests. The sensor physical range, the expected measurement range, the expert-based local frequent measurement range, low or high absolute gradients, absolute uncertainty, relative uncertainty of your data, if you have redundancy, and if you have outliers in your data set. And I will explain in the next slides a few of these tests. The first one is really obvious. Huh? It's the sensor physical range. So for example, I have a water level sensor measuring between 0 and 2 meters. So all values between 0 and 2 should be valid. If in case you find negative values or values above 2, they are rejected. So in the range, the mark is 1. Outside the range, the mark is 3. And maybe if it's surprising, sometimes it happens. It happens when in this case, we found 0 or negative values of water velocity. And we know for physical reasons that it's just impossible. A very important point here is that this data validation is not made on the sensor output. It's made on the data you have collected in your data logger, in your SCADA system. So we validate the complete chain from the sensor itself to the transmitter, the converters, and analog to digital data value, etc. So we should always work on the complete chain. This is why sometimes we disagree between manufacturers of sensors who claim that they don't need calibration or the uncertainty is 2%. But when we have a complete chain with all the steps from the sensors to your final data file on your computer, you have many steps and many locations where uncertainties and errors can be introduced. This is why it's very important that this validation is applied to an entire chain of data acquisition and not to the sensor itself. Local frequent measurement range. This is a very important assistance for data validation, but it's something you cannot generate from the first day of your monitoring campaigns. It's based on data and information you collect progressively. So for example, imagine that after 1 or 2 months of measurement, you have collected data on your in a sewer. Then you can make a pre-validation based on your first feeling. And if they are valid, then you can define, for example, a 95% confidence interval. So in my local measurement point, what are the most frequent value, for example, of my pH value? And in this case, it could be between 6 and 8. So if the values are measured between 6 and 8, they are expected to occur very frequently in this monitoring location, and they are validated or accepted. If you are out of this range, but still within the physical range of your sensor, we declare that these values are doubtful. They are unusual, they are infrequent, but they are not physically impossible. But as they are very infrequent, we recommend the user has to make a final decision to say, okay, maybe my local range was too narrow and progressively I have to widen it to include more values. Or on the contrary, if at the end you approve the rejection, maybe you should adapt your local range progressively. The idea is you tune your parametric tests until they behave as an expert user would process for the data validation. And this is an iterative process. You cannot set all your values at the first day of your measurement campaign. But This is also another reason to have these successive files, so you can go backwards as you acquire more data on your monitoring sites, monitoring sensors, and so on. Sensor redundancy. Now, when you consider globally monitoring in sewer systems, the most expensive is the cost of human resources. It's not the cost of the sensors. So if it is very important, for example, to know key variables like water levels, discharges, pH, we recommend that you double the sensors. If this value is very important, it's important that you pay enough to increase the probability that you always have a good value. And if you have sensor redundancy, you will never have exactly the same value. So we need to apply some specific tests. Are my values consistent? So imagine you have one sensor, for example, measuring water level, another one just nearby, measuring also the same water level. Then you calculate the difference. And on a moving time window, you analyze the difference between the two sensors. And if the difference is compatible with the uncertainties of both sensors, then your conclusion is the two values are not significantly different, and you can validate both of them. If the moving mean is beyond the acceptable difference and cannot be explained by the uncertainties between the two sensors, at least one of the sensors generates wrong data, maybe both, but at least one of them. And then you will need to go into the details, analyze, go on site, check your sensor, which one is generating this unrealistic data. So sensor redundancy is a key point, and it's very important to increase the reliability and the availability of valid data in your system. In this case, it's, I would say, physical redundancy. It's two sensors, but you can have a kind of analytical redundancy. For example, I have a sensor measuring the discharge in my sewer system, and then I can generate a virtual sensor. Number two, for example, I have measured the rain, and with a model, I can predict the discharge in my pipe. So I have a predicted discharge, and I can compare it with a measured discharge, exactly with the same tool. And if I know the uncertainties of my sensor, and if I can evaluate the uncertainties of my model, then I can compare both and check the difference and say, okay, the difference is compatible with the levels of uncertainties on both sides, and there is no significant difference, and I will validate my sensor because, for example, the discharge is compatible with the rain events we have measured. In case the difference is too high, then you have to go back. What is the faulty source of information? Either the rain was wrong, so if the rain is wrong, you generate a wrong discharge, and the measured value was correct, or it's the opposite, the rain was correct, and you had problems with your discharge meter. And just an example to illustrate this, it's another pipe where we had measurements years ago in Lyon. So the blue line is the water level over a number of days, and the red crosses are the flow velocity. And you can see these flow velocities in this figure. And how to validate the flow velocity, because we assume at the moment that water level was validated and we can trust in the water level. If you take values from the previous weeks, months, or years, you can generate this figure. And you see that there is a good correlation between the water level and the mean flow velocity in meter per second. And we have established this purely empirical model, so there is no hydraulics reasoning behind. It's just based on validated data sets on this site for both sensors. And from these both validated data sets, we can generate this estimation of the correct velocity for a given water level. And if we go back to our figure, for the blue water level, this is the estimated or the predicted flow velocity. And you can see that during some periods, the predicted and the measured velocities are consistent. There is no problem. During other periods, they are completely different. For example, in this period, we completely underestimate with the measurement the predicted values. In this case, it's the opposite. We are much higher and with lots of noise above the predicted values. And we can compare the predicted and the measured values and calculate the residues, which are the differences between the predicted signal and the measured one. And there are periods where this is too far from zero, according to the respective uncertainties of the measured values and the prediction. And we can identify periods automatically during which there is a big discrepancy, a significant discrepancy between the measured and the predicted value. And again, if we trust and have good reasons to consider that the water level is reliable, then we can conclude that during these periods of higher residues, there is a problem with our flow velocity values. And then we have to investigate why do we have this problem. And now we will illustrate this with the UDMT software developed in the Co-UDlabs project. Just before Christmas, we had to make some deliverables in the Co-UDlabs project. And in one of the work package of the project, we tested some sensors. And during a number of months in 22, we tested a PAH, polycyclic aromatic hydrocarbons probe. And I will illustrate the use of UDMT Toolbox on this sensor. And we tested it in a catchment in Lyon, which is part of our field observatory on urban hydrology. It's the Chassieux catchment located in the eastern suburbs of Lyon. So on the left side here, you have the catchment. The total area is 185 hectares. It's an industrial area. And at the top left corner, you have in this white triangle, you have the Django Reinhardt storage and infiltration tank. And all stormwater and runoff collected on this industrial area is discharged first in the settling tank, and after settling, the water is infiltrated in this second tank. At the inlet of the settling tank, we have a monitoring station, and we have here the flume, where we have our sensors measuring water levels, flow velocity, pH, turbidity, conductivity, and a few other values. And during a number of weeks, we also added this pH probe in the same monitoring flume. The purpose today is not to evaluate if this sensor was satisfactory for our needs or not, but just to illustrate how we can use the UDMT toolbox with this data set. So this is the estimated concentration in pH delivered by the sensor in microgram per liter during the test period from the last day of May to end of December 22. So we have these values, and we have one measured value every 2 minutes. And for today, I will use a sub part of this dataset just to make the demo running faster than the complete period of 6 months, located at the end of November. So what we need for using the UDMT, as I said before, we need file in a very well-defined format. So the format is based on columns for CSV file. The first column is always the time with this type of syntax of format. Then the column number 1 after time is the pH or the concentration value in microgram per liter. And then we have the uncertainty also in microgram per liter. And this uncertainty is based on the fact sheets provided by the manufacturer. And we have this data. You see only here a few lines from May to this or first days of June to end of December 22. And I will show you in a few minutes the online demo of the UDMT for this time series. But before we can run the tool, we have to define our tests and the numerical values we want to use. And you have to declare, when you use this software, you have to declare the different tests we are using. So you have here the 8 tests I have presented before. In the case of this demo, I will not apply all of them because we don't have the necessary information for all of them right now. But we will use these ones, the physical range. So when you read the fact sheet of the sensor, it's written that this sensor has a range of 0 to 500. So we have defined the physical range as 1 to 499, which means that all values below 0 or below 1, 0 or lower, and above 499 will be rejected as unrealistic or doubtful. Then we did some additional experiments, and we expected that in this location, it's more or less impossible to have less than 5 and more than 250 microgram per liter for this sensor. This is based on some previous investigations, other data we collected during the previous years. So values outside of this range are more or less impossible to be observed there. But however, when we increased our investigations, looking to some campaigns carried out during more than 10 years in this catchment, we can say that, okay, this is possible, but this is not very frequent. So the expert, knowing very well this catchment and the activities on the catchment, because it's an industrial area, will say that, okay, between 10 and 150, it's probably the most frequently observed values you can expect. Then we introduced a test based on the gradient. So the idea here is to automatically detect, I would say, the flat signal or very sudden fluctuations in the signal. So we have a value every 2 minutes. So we defined 2 values. A minimum gradient, in this case, it's less than 0.001 microgram per liter per minute. So all gradients below these values will be considered as flat or almost flat signal. So there is no changes over time, which is strange. And when the gradient is higher than 20 microgram per liter per minute, it's also very unlikely that the value can change so rapidly, even if it's changing between dry and wet weather. So it helps to automatically detect these very quick changes. Absolute uncertainty, we have not applied this test, but we decided to apply the relative uncertainty. So if the value is measured with a relative uncertainty higher than 25%, we consider that this is too much and we don't want to qualify this data as valid. Of course, you can discuss all these numbers we have selected for a while. It's based on local expertise, local knowledge, and you can start with these values, for example, and after 1 to 6 months of measurements, then you can refine, reprocess your first data, and progressively you will be able to generate reliable data sets. And all these values and thresholds have to be introduced and written in a CSV file with the first column named T, like thresholds. And for each test, you have to define the minimum and maximum values. And you can observe on this extract, on this copy of the file, that the test can be applied to the measured values, but you can also apply some tests to the uncertainties of your values. And sometimes the uncertainty is not constant. It depends on the absolute values. So we can also decide to qualify or reject data based on their uncertainties. And once all this is defined, you can process your file and run the tool. Okay, it's time for the demo. So I will switch to the tool. So this is the interface, as I said before, quite simple, not too complicated. So I will go for data validation. I have
see your screen, Jean-Luc, I think.
Sorry?
We are on your PowerPoint.
Yes, sorry. Yeah, thanks for letting me know. Oops. It's okay? You see the app?
Pas encore.
Mm-hmm.
Peut-être.
Yes, you should stop share screening and then share.
Yeah, I will start again, but okay.
That's what it is.
Just before it was working, but...
C'est plus sûr.
Yeah, okay, let's go there. It's okay?
Yes.
Okay. So this is the user interface. So you have to choose data validation first, and everything is based, you have only one box you can select. So you are guided step by step through the use of the tool. So I have to choose one time series. So I have this data set. And it's systematically displayed on your screen. So you can check, yes, this is really what I wanted, to avoid that you don't pay enough attention. So you have the time, the value of the concentration, and the uncertainty. Okay, it's what I want. You click OK. Then you are invited to provide information about the thresholds you will use. So you have a file. You have the different thresholds I have introduced previously. So you can check, read, confirm that this is what you want. Two other things I will explain very briefly. It's the redundancy matrix. So the redundancy matrix is simply a matrix full of zeros, and you have only to introduce one when two sensors are redundant. For example, if I have not only the pH concentration, but if I have also two water levels, I have to indicate this water level number 1 is redundant with water level measurement number 2. And this is how I indicate in my tool that some sensors are redundant, and it will be used in the data processing. But in this case, we have only one sensor and nothing is redundant, of course. So it's full of zeros. And the last is the uncertainty matrix, in which we have to declare the correspondence or the link between the sensor and the uncertainty. So in this case, I have only one sensor, so it's obvious that the uncertainty of the sensor is correlated to the sensor itself. But it happens, for example, in some cases, imagine you have a multi-sensor multi-sensor probe. You measure simultaneously, I don't know, pH, conductivity, and temperature. pH and conductivity sensors have a correction based on the temperature measurements. So if you have uncertainties in your temperature, it will have some influence on the uncertainties of your pH and conductivity. This is where you can introduce this kind of information. In our case, it's very simple, so I click OK. And now you have to select what you will apply. So I will tick the different tests I want to run. So physical, measuring, expert, gradient, and relative uncertainty. And you have to make a final choice. At the end, you will have a collection. In this case, we will apply 5 different tests. And what is the way you deliver a global grade or mark? And we suggest 3 options. Either you tick the worst. So I have different tests, and I consider that the global mark for my data is the worst case. Or you can calculate the mean. So you have different tests with marks from 1, 2, and 3, and rejection or acceptance rate. So you can calculate the mean, and you will say this is the mean value, which will be the global assessment. Or you can decide to go for the median. There are different options. This is why we propose the 3 of them. It's the user responsibility to make a choice according to his needs and his requirements. But for example, let's keep the median. And then you run calculate. In UDMT, you have always this green progress bar. So when everything is finished, you know it. And then you can have a look. For example, if I look at the physical grade range for my concentration, you see that everything which is good is marked with a green triangle, and all the rejected data, here in this case, they are equal to 0, are rejected. You can have a look at the, for example, the expert range. So if I would be the expert, I would say that the value which are completely flat here at the bottom are unrealistic, too low. And these values are above the 150 microgram per liter threshold I have defined before. So all values here are considered as doubtful, as, oh, maybe it's correct, but it's very, very rare that you will find some high values like that in this location. So please go and make a final manual validation. So you can check test by test. What are your results? Here you have the gradient. So here the signal was flat. And here it's doubtful because the peaks are too high. You jump from one value to the next one after 2 minutes with a gradient higher than 20 microgram per liter per minute. So you are invited to pay attention to these values and why it happens. Here on the top of the figure, it's green because we have two values in a row close to 500. So between these two values, the gradient is in the acceptable range. So it's marked as a green value. You can see that only, of course, if you zoom on the figure. Oops. Okay, I'm sorry. It's not the right moment to do it, but you can do it. And also the relative uncertainty. You see that all the low values are highly uncertain. The relative uncertainty is higher than 25% of the measured value. So if I would like to have such a sensor, and if I cannot have an uncertainty which is lower than 25%, I can ask myself, okay, is it really worth to use such a sensor? Because my knowledge will be probably not good enough to derive some good conclusions. But it depends on your own objectives. What do you want to do with the values delivered by this sensor? If you want simply some warnings, if you want some alerts, it may be sufficient. If you want to calculate loads, for example, during storm events, maybe your uncertainties will be very high at the end. So the knowledge is poor. If you want to know, for example, the dynamics of a process, maybe you are more flexible and can accept, okay, my uncertainties are significant, but I have an idea of the dynamics, so it can be satisfactory, for example, to compare with a model. So your decision and the thresholds of your test are not defined in absolute sense, but depends on what you want to do with your data, of course. And you can also check the final global values. You have here the reminder that it's based on the median value. So you can observe here that according to the median values, all the green triangle correspond to validated data. The yellow ones require a final manual decision, acceptance or rejection. As I said, everything is transparent. So at the end, if you click on download results, you will save the file. Okay, I did it before, but I can do it again. I will share my screen, and if we open the file, you have in the file, you find again the time, the values, and the uncertainty of your sensors. And there, for each test you have applied, you have the mark given by the sensor, and you have the global mark. and you can process with all your data like that. So everything is transparent. You can analyze case by case your data, and then you can use another tool to make your final manual decisions or so on. Okay, that's the end of my demo for the moment. I have to go back to my last slide. Whoops. Okay, do you see my... I was there before?
Yeah.
It's okay? Okay, so it's time for questions, and François and I, we are available for your questions if you have any for the last minutes of the webinar.
Thank you both. And I see the discussion with Sadashif was concluding. Do someone want to have any question or oh, Min, do you want to open your microphone and ask their question? Thanks. And what's your name?
Nice to see you.
Hi.
This is Min, Jean-Luc and François.
Nice to see you.
It's very interesting talk and topic. I mean, we have been working with this kind of monitoring for sewer system a lot. And actually, I see that we have faced a lot of more complicated problems, you know, like sometimes they, due to different, maybe, you know, the real you know, dynamics of the sewer, hydraulic dynamics of the sewer, or because of the erroneous, you know, like of the sensors, you know, or due to the sediments whatsoever. There is always a very, very different, because we measure like water level, we measure flow rate, and because like yeah, the Sadashivi is working on the data, and I think they are quite, you know, they feel frustrated because the data is so much complicated. Because in our situation, we got where you have also like overloaded source system, which means that you have like four pipe flow, always a four pipe flow with high water level. And then sometimes that the sensor, you know, the flow rate is 0, but actually, but you didn't, but if you look at the water level is changing, right? The water level is changing, but the flow is 0. And sometimes it's jumping, you know, some very complicated situation. So that's why I think that's, we really need some very advanced technique to find out, you know, the reason, or, you know, to the outliers, also to find maybe they look, sometimes it's like it looks like an outlier, but maybe it's not, it's correct, maybe, you know, because it's just we didn't understand the hydraulic situation.
Yeah.
And for example, there might be, because in some situation I was questioning that maybe because the flow rate, because we have a 4-pipe flow, which reduced the flow velocity. Therefore, you know, it was out of this sensitivity of the sensor. Therefore, that it appears to be 0, but there is still some like very slow flow there, you know, because the water level is changing, right? So I mean, so I think that it's really a very interesting topic when we look into the data. But I think that we really need more advanced, you know, more complicated technique to solve these data issues. And I'm thinking maybe with the help of like kind of like a machine learning, you know, we can, you know, we can find some solution for that, because we got some observed data. Because we have in one of our projects, we have installed more than about 300 you know, but it was a big network, and we have 300, more than 300 points of observations, but the data is very, very complicated. But I think that I really wanted to show the, you know, pop up this problem so that we can, you know, you know, I think that there is quite some people in this webinar, and I hope that, you know, we can work on this together, you know, to get something even, you know, enrich this topic, I would say.
Yeah, what I've presented today, I said it's the basic.
Yeah.
For some sensors, but then you have some work to be done upstream, I would say.
Yeah.
Usually you come in a sewer system, you don't know, you have no information. You have your IDs. And frequently we have seen that our IDs of the hydraulic behavior in the sewers is wrong. And so I said, even the monitoring itself is iterative, okay? And I always recommend, okay, don't start by installing very expensive and fixed installations. Start with something flexible to have a first idea, what are the ranges of variations of my signal? Do I have something I can measure? And sometimes, in some situations, we should admit or recognize that there is no sensor to measure accurately what is occurring. If you have very more or less stagnant water, all flow meters or flow velocity meters will fail. So it's not, and you can introduce all the artificial intelligence you want downstream. If you have no proper data which is representing properly the process, there is no added value. So you should always check that your sensors are relevant and appropriate for these specific conditions of flow and hydraulics. And it's not always easy, I should agree. Then you should always calibrate, check, go regularly on site. And then the data validation tools I have shown today are only the first ones. Then you can have much more elaborated methods to compare, for example, upstream and downstream locations. For example, this is how, with a colleague, Mathieu Lepeau, we found in Greater Lyon some unrealistic values. And we discovered later on that it was due to the position of the sensor in the sewer, which was wrong, generating a misinterpretation of the velocity measured by the Doppler. So we need to investigate. Sometimes when you have strange values, you have to do like a police inquiry. Who are the suspects? But you cannot, it's worthless to validate data with any kind of algorithm if you are not sure that your sensor is not appropriate for your needs and your local conditions of flow. That's a key point.
I can add something to this because you're completely correct, Jean-Luc. But I've been looking into artificial intelligence for data validation. And the big issue is, first, you need to have a big database of validated data by people. And this is specific to a certain system. And on top of that, even if you got it trained correctly and something weird happens, like what Jean-Luc showed, this experimental flushing, that is not in the data set for which you train the model. So I guess you can, to a certain extent, replace human interference with an AI model, but I got some serious doubts. However, I've been wrong many times in AI, so let's see what happens in the future. But for now, I would advocate against it.
There is a specific question. I'm sorry. There is a specific question on how or what you can do to replace a missing value in the case of redundancy. From Fabienne. I don't know if she wants to precise the question. Is there a magic solution or a scientific solution?
Oh, well, yes, there are several. And what you can do, for instance, is make a kind of voting system. So what Jean-Luc showed, you got two sensors, and then you can have this algorithm to decide, okay, one of them is wrong. But if you got three sensors, they can vote one out.
Yeah. If you have only two sensors, you can detect a problem. You can't solve it easily. But if you have three sensors, why? Because if you have two sensors, make it much rough. If you have only one sensor, you have to trust in it. You have no alternative. So if you have two, if they are redundant, if they are consistent, you are happy, you can trust in your values. If there is a difference, then you need to investigate which one is wrong. And in our O2 monitoring stations for years, we had two values. And after months and years, we were able to know that this one is more reliable than the other one, but it's based on long-lasting experience because of these sensors in this location with this maintenance. And when you have two sensors, you have two values and one equation, which is the difference between two. And you can't solve one equation with two unknowns. But when you have three sensors, you have three differences. One with two, one with three, and three with two. And in that case, you have three equations and three unknowns. And mathematically, you can solve it and find which value is the most unlikely one. But so redundancy starts from two, but you can go beyond. At the moment, in one of our sites, we have 4 sensors just for test. But we are testing a very low-tech radar system. We are measuring also with a new laser system. Each of them costs 200 euros. So you can make redundancy. The high cost is not the sensor, it's the human resources I mentioned already.
Strictly speaking, you could have 3 completely different measuring systems, because if you've got 3 sensors on the same data acquisition system, then you can't be certain that this voting system will work out correctly. But
yes. Yeah, there are. So there are solutions to this question. Then it's the good solution is a case-by-case analysis.
Yep.
Is there any other question? There was a question on which parameter it was available, but Abby answered and said it's okay for every parameters.
No,
Or not?
I'm not sure for every parameter, because if you're looking at vector fields, for instance, that's a bit of a different story. Like I showed these PIV results. So vector fields of flow velocity, these are quite difficult to validate. And I'm not sure, would you be able to analyze vector fields in this tool, Jean-Luc? I don't think so.
Yeah, so it's valid for single values in time series. Yeah, but for example, the question is flow rate. Yeah, flow rate is simple.
Flow rate,
yeah, of course.
Yeah.
It works well for flow, water levels, pH, conductivity, turbidity, all this kind of
series, basically.
Then if you have information based on long vectors at each time step or matrix, it's becoming more complex. But the problem is, as François said at the beginning, when we observe the global practice in our field, even the 5, 6, 7 basic tests are not systematically applied. So before we think about very advanced tools, okay, start with the basic ones to be sure that we do not apply advanced tools on poor quality data.
Exactly.
Okay, so for the conclusion, we invite each participant to go on the website and use his data table and test it immediately to be used to. That's it. And then you can contact, you have a contact address. We will give you again this contact. If you have any problem, just explain what's your problem, and Jean-Luc will try to answer or to help.
Yeah, we plan to have the last release 25A, probably in end of February or March.
Okay. Abby has a question. When is the raw code available? It's already? No?
No. We wait until the end of Co-UDlabs because, yeah, we have already got some feedbacks. So we made some modifications. 2 months ago, I made another modification just to make something more appropriate for the gradient test, for example. So we don't want to make the code available until before the end of the project, but it will be available in April. It's a MATLAB code.
Okay. So is there any more questions? It's time. It was very clear. I understand everything with my good English. So I suppose everybody understands, but the good question is to go and use the tool. I think that's the most important. And perhaps we will have some other opportunities to exchange with users. Do you want to give some few words to finish? François, Jean-Luc?
Oh yeah, it was quite nice. And well, if I saw some questions about data standards. So if anybody wants to, like Fabienne, she seems to have a bit of an issue with data standards. If she wants to have a private talk about this, she can contact me. That's no problem.
Yeah, it was Fabienne and I think
For the rest, a very good weekend, all of you.
Annette.
Yeah.
Okay. Thanks both. Thanks to all of you to assist and to be interested in data validation in urban drainage. And that's very important. And really, we need to have these exchange times. So thanks both. Thanks to everybody. And we will send you the presentation. If you were registered, if you were not, just register. I don't have your email if you didn't. Okay.
Thank you.
Thank you.
Okay.
Bye-bye.
Bye-bye.
Bye-bye. Thanks a lot.